waves that propagate and reflect from boundaries that's allowed. Propagate through and reflect from boundaries and propagate through materials. And some portion of this lecture is going to be really hand-wavy, where I'm just trying to give you an idea as to what it is that controls the behavior of waves as they pass through materials, and some of it will be reasonably rigorous. Right? I think I'm going to start off with the idea of the dielectric function and the index of refraction, and how it is that that could be what it is, how waves behave. So you're used to thinking of the dielectric function as being something that has to do with the polarization response of a material. And the reason that I call it a dielectric function is because it can depend upon frequency. It's not just a constant at zero frequency. And we already know that there's a relationship between the polarization of a material and the electric field that's applied, which is related to the dielectric constant of the material. So I'm just going to state for the moment, but we'll come back to it later, that the dielectric constant can actually be a function of frequency. And I'll talk about a little bit about the microscopic mechanisms that give rise to that. But what I want to do right now is give you an idea as to how polarizability of materials, polarizability of molecules, gives rise to a change in the apparent speed of light as it moves through a material. So let's say I've got an atom here, an atom here, and that atom has got some quantum mechanical electronic cloud around it of electrons. And we talked a little bit about the polarizability of the material. We apply a field, let's say in this direction, the nucleus moves this way, the cloud of electrons moves that way, and as a result we have a dipole moment for this material. So I'm going to get a little bit ahead of some of the material in class right now, hence the hand waving. What we can say about this material here, this atom here, is that when we come in with an oscillating electric field, then this atom is going to respond, but now I'm just going to say something. Sometimes it can't respond fully in the time that's allocated to its response. If I applied an electric field at zero frequency here and just turn the field on, then I would get a certain dipole moment, let's call that the dipole moment at zero field, all right, which we could deduce quantum mechanically. But if I oscillate the electric field that's propagating along this direction, if I oscillate it quickly enough, then the dipole moment of the molecule or of the atom doesn't have sufficient time to respond. So let's say if I had a response at zero frequency which was that large, then at a much higher frequency I may get a response which is only that large because it doesn't have time to fully polarize. Now those frequencies have got to be rather high in order for it not to have time to fully polarize. And these frequencies are of order of the electronic excitation frequencies, which are something like 10 to the 15th radians per second, right? So that's not a symbol, that was an arrow, right? So the frequencies are very high, and at very high frequencies, the atoms don't have time to fully polarize. But wait, there's more. If you have an oscillator, and you drive an oscillator at a frequency that is above its resonant frequency, then actually that oscillator lags the frequency, the wave that you're driving it at. So let's say I have an electric field that looks like this, and the atom that responds to it is going to respond with a little bit of a delay, and it's an arbitrary scale, but I've got my polarization here. And my polarization might look something like that. All right? Now's the bit that I haven't told you much about yet, which is that if I have a dipole and it oscillates, then that dipole radiates. So field give rise to local polarization. Local polarization gives rise to an induced field, not the Faraday-induced field, but an electromagnetic propagating field, which results from that polarization. So I've taken an electron, let's say, and I'm shaking the electron up and down, right? And then that electron radiates because it's being accelerated up and down, right? So the induced field, what comes out now, comes out, I'll be probably not strictly correct here, but I'll draw it like this. I'll call that the radiation field, right? In fact, by the way, that radiation field from that atom there goes out in both directions. I'm just oscillating the atom. The atom's going to radiate in all directions, actually. We've got to take special care and look at how the radiation field from this atom is related to the radiation field from that atom, is related to the field from the next atom down, right? And these atoms, this atom is going to be delayed by the speed of light with respect to that atom, and this one's going to be delayed by the speed of light, actually even more than the speed of light, with respect to that atom. And this atom over here is going to be ahead. And then when I add up all of the radiated fields, that's going to be the result now, the resultant. I add up the whatever remains of the original field, because the process of the original field interacting with that atom gives energy to the atom, which is then re-radiated. So the original field decreases in amplitude a little bit here, and I have a radiated field. Decreases a little bit more in amplitude here, and a radiated field decreases more, and I have some more radiated. Okay? So the original field is depleting, and the radiated field is increasing as I move through the material. All right? But wait, there's even more. All right? The field that results from, let's say, this atom here, this might be the first one in the sequence, is now going to be the original field. Let me draw the original field. Okay? Plus some radiation field from this guy here. Smaller and delayed. So the field that this atom sees appears to be phase delayed, because anytime that I add two waves of the same frequency, I have superposition of the two waves, the resultant of the two waves is going to have a phase which sits between the two waves. So even if this is very weak, this wave is going to end up delaying that wave just a little bit. So the effective wave that I get here now is maybe something like this, which is delayed. Not all the way, but delayed just a little bit. So this atom experiences a delayed field with respect to what it would have had if that atom weren't there. All right? That's a phase delay in the field. It's as though the wave has traveled more slowly than it did originally. Next atom introduces a little bit more phase delay. A little bit more, a little bit more, a little bit more. So the speed of light actually remains the same. It's the speed of light, 3 times 10 to the 8th meters per second. The electromagnetic wave that's propagating through this material, the one that actually propagates, and is not the result of re-radiated radiation, travels at the speed of light. But each one of these atoms effectively adds a phase delay. And that's actually what we mean when we talk about the speed of light in a material as being the phase velocity for a wave in a material equal to the speed of light divided by the index of refraction. Okay? So that's the conceptual bit. Yeah, Adam.
What happens if you do drive it at the resonance frequency of the material?
I wish, I actually had intended to and then decided not to because I forgot why I intended to do it. I had brought my computer with me because I had the full dispersion curves. When you drive at the resonant frequency, let me see, I might have it drawn here. Yeah, I do. So we actually look at the magnitude of the polarization. Then actually, I'm going to answer your question in a couple of minutes because I'm going to use terminology here that I haven't yet introduced. So I want to introduce some of the optics terminology and then dielectric function terminology, and then I promise I will answer your question if you ask it 3 more times at the appropriate time. So if we really want to understand the optical properties of materials, we actually have to first understand the quantum mechanical properties of atoms and their response to an applied electric field. We're not going to do that in this class. I'm going to give you a classical model of what's going on. And then I forgot what else I was going to talk about. So I will just go on. All right. So let's say we have a window. And then the window's got some thickness. And on the other side of the window, I have a person. And then we ask what happens when we put different materials in that window, all right? We have good experience with what happens when we put a transparent material. So to characterize materials, we have transparent, we have, let's call them at a particular frequency, opaque, absorbing, and we have translucent. And what translucent materials do is they typically don't absorb, they scatter. So light that comes in interacts with the material, but there is no loss in the material. The light is re-radiated or scattered, and as a result, there's no overall loss in the light, but information is lost as the light passes through because it doesn't pass through in a straight path.
Frosted glass?
What?
Frosted glass, or is that opaque?
That frosted glass is translucent. It passes light, but it doesn't pass light in a straight path. It scatters. Let's see. I guess there's one more characteristic I want to put in here. We can have a reflection at a surface. Okay, and I drew that picture for no reason whatsoever. Actually, the reason that I did was I was thinking of it was that in the slides that I was going to actually use for projection, I had Stickman behind the window waving and then had various materials that we slide in with different optical properties which make him invisible to you. So if you wish, when I post this online, you can go look at the PowerPoint slides and you'll see him waving.
So
All right.
that's just a shameless plug to go look at the notes.
Yes, if I post the notes, then you should look at them.
You posted them last time.
All right, so I didn't post these notes, did I? I post notes whenever I think of posting notes. And no, I need to think of posting notes, I need to have my computer in front of me, and I need to have access to the interwebs.
Yeah.
So in other words, I should remind you when I go back to get an extension cord for this.
Yeah. Oh, and there should be no one else in the office to distract me. And no food, just sitting around. All right. So I said that it was the dielectric function that's going to be important when we talk about the re-radiation of light. So I want to describe the properties of this material that sits here in terms of the common words that we use and the dielectric function. So transparent materials, there's not much, oh yes, there is something to say, which is that these materials, like glass, will have an observable index of refraction. There's no material that's perfectly transparent that I know of. There's always some form of loss, but usually the loss can be very small. And in, for example, optical fibers for communications, you can send an optical signal down the fiber with a loss of something like 1% over a distance of several kilometers, let's say 10 kilometers. So that's extremely transparent material. It's actually transparent, has that transparency only at the wavelength that was designed for. Other wavelengths, there'll be other losses. Go to shorter wavelength, you get scattering, and other infrared wavelengths, and you get absorption. But an absorption coefficient such that you can go kilometers with rather small loss. Which brings me to the absorption coefficient, which is usually written as alpha. And when I'm transmitting through a material, we would use, if we were going to make a measurement, we would have the incident intensity, and then we would have whatever loss there is. Now this is not going to be exact for the one person in the room who knows the difference. I've got two surfaces. Oh, actually, let's see, the transmission is going to be, yeah, no, 1 minus the reflection at one of the surfaces squared, right? Times, so this gives rise to reflection. We'll talk about reflection here. Times e to the minus alpha d, where d is the thickness of the material and alpha is the absorption coefficient. So if you want to measure the absorption coefficient, you do it in this way. You measure the transmission, you measure the beam before and after you have put the material in, you measure the reflected beam, and you measure the incident beam and the transmitted beam and deduce the absorption coefficient from that. Normally you do that for different thicknesses and deduce alpha from the slope as a function of length. For the chemist in the room, that's called Beer's law.
Alpha is called the molar extinction coefficient.
Yeah. We are going to generalize here.
Any
Translucent,
chemical-
we're not going to worry about it, but I will tell you the thing that characterizes a translucent material is the index of refraction. I'll put the index here too, and the so-called scattering coefficient or scattering cross section. Right? We're going to use sigma again later for conductivity, so just keep in mind that that's a scattering coefficient. And for reflection, I need the index of refraction primarily. All right. So we have this thing called the index of refraction, which related the speed of light. actually not the speed of light, the phase velocity of the waves passing through the light, through a material, to the speed of light itself, right? And now you see I've got this alpha in here, which gives rise to loss, and the index of refraction. Normally, we describe the index of refraction as just being the real part of the optical constants. But I'm going to generalize now, and I'm going to say that the index of refraction can be complex. It can involve loss and phase change. So the real part of the index of refraction gives rise to the phase velocity, the phase change, and the imaginary part gives rise to the loss. And so this is frequently written then as, oh, yeah, I should tell you, that's the square root of mu epsilon as Ohanian uses it. Dielectric function permeability. And that is frequently written as n plus, and that's this, now the next, whether it's plus or minus, depends upon preference, actually. But I'm going to write plus I kappa. This thing here is called the extinction coefficient in the absence of scattering. It's the extinction coefficient. And normally we don't write it fully that way, we write it like this, which, if I figure out what this has to be for a transmitting wave, oh, what do I want to write here? Yeah, let me come over here. The electric field, as it transports through the material, could be written as the electric field amplitude e to the I kx minus omega t. All right, actually, I'll be more complete here and write k dot x. All right, k is the wave vector of the light. Yes.
Is E not supposed to have a vector on it?
Yes.
Okay.
It points in a particular direction, and then the wave propagates along like that. All right. So the vector tells you what direction the field points, what axis the field is pointing along. Right? That k there points in the same direction as the pointing vector, so I won't put a vector on it right now, is equal to 2 pi complex value of the index of refraction divided by lambda, I'll write as lambda naught. That's the vacuum wavelength of the light. So you're used to seeing it as 2 pi over lambda. And you may have seen in physics 2, this written as 2 pi n over lambda to describe the phase shift. But actually the k that goes in there can be complex. And it's going to be that complex value here. And so then if I want to map that onto alpha, I could look at this and I could say that the field here looks like e to the I 2 pi n over lambda naught x. I'll just worry about the x part because the omega t has remained unchanged. Okay? And n, remember, was n plus I kappa. So I'm going to end up with e to the I 2 pi n over lambda x plus, times e to the minus 2 pi kappa over lambda x. Just multiplying it out. I got an oscillating term for which the phase shifts. So I've got the phase velocity in here, all right, and a decaying term. So the electric field is decaying. If I want the intensity is proportional to the field squared. It's the pointing vector, and I'll just worry about how things go here. So that means that the intensity will be proportional to e to the minus 4 pi kappa x over lambda, which I told you for an absorbing material, we can write as e to the minus alpha x. So that tells us that alpha is equal to 4 pi kappa over lambda. And people write they switch back and forth freely between these terms. Optics books will probably use predominantly alpha and occasionally refer to kappa and lambda. Electromagnetics books will always, well actually they won't even use this terminology. I've got to go back now to talk about the other terminology that comes in here, which is related to the fact that I wrote that, okay? For most dielectrics, mu is about 1. So that tells us that the complex index of refraction is the square root of the dielectric constant, or dielectric function. I square both, but let me write that out. That's equal to n plus I kappa. So I'm going to square both sides, and I end up with the complex dielectric function is equal to n squared minus kappa squared plus 2i times 2n kappa. All right? This is frequently written as the real part of the dielectric constant and the imaginary part of the dielectric constant. I have to say that I've actually never found a textbook that puts all of that on 1 or 2 pages, or even in one chapter. What it'll do is do part of it somewhere and part of it somewhere else, perhaps. So this, I actually end up frequently referring to my own notes when I'm doing calculations, because this is the only place where I've put it all in one place. All the useful stuff is put in one place. Okay, with that introduction, in the next part of the class, I'll talk about dielectric functions, and then I'll talk about propagating waves, but we'll take a break now.